let's get into it, I guess. So we're going to be talking about designing custom studies to assist with the challenges of modern energy planning. Here's the agenda. We're going to be introducing sort of the challenges that the energy industry faces in the modern climate. We're going to be talking about what granular studies are and how they address those problems, and then we're going to cover the scope of the work that we've done for companies already. After that, I'll be handing it off to Dr. Brown. He'll be talking about how we transform bills into daily data, give some examples of studies we've done in the past, and then we'll close it together talking about the support we give and then answering further questions. All right, next slide. All right, we're going to go into the introduction. The first part, which is about challenges in modern energy planning. This section is our hope to lay the foundation to help everyone understand what's coming. So I'm hoping that when you see this slide in this list, it speaks true to what you're experiencing on your side. I wanted to make a list that includes the biggest hotspots that I notice and that we get asked about to help develop custom studies to address these problems. So these challenges are all complex, they're interconnected, they're not only national but regional. And so a lot of, like I said, the work that we've been asked to do focuses on addressing multiple of the challenges on this list. So we try to collaborate with our customers and innovate to try and find effective solutions to address these problems. This is the reason we stay involved with research, like Tom said, and it's the reason we come up with new studies, because these problems are always changing in the nature of each grouping and pair, and the way that they're complex and connected is always changing as well. All right, next slide. So here I'm going to be talking about the geographical data or detail and data. So this is kind of going to give some background on the studies we've been doing in the past. Historically, we perform these studies on operating areas or op areas. So these are geographical regions with a relatively fixed set of customers fed by one or more gate station. So the op area in the past has been some of the most detailed geography we're able to use. In this graphic below, I'm going to walk you through sort of how we would define op areas. In this first graphic with the two clouds and the two diamonds, Dr. Brown, would you mind putting a laser pointer or something over there? Thank you. Just to help show everybody what I'm talking about. So in this scenario, we'd be talking about one or two op areas if each of those diamonds was a gate station or a measuring tool on a pipeline, right? So you could either add them together and make one operating area, or because we have data of what's going into each cloud, they could be two separate areas. In the second image, even though there's two gate stations, if the gate stations are those diamonds feeding into this cloud, it could only be one op area, right? So we can't really see what's going on because we can't tell who's using what part of those gate stations gas that's going into the cloud. On the third image, it looks different, but it's the same. It would be the same in terms of geographical data as the second cloud, because even though there's two separate, let's say, neighborhoods that are connected by a pipeline, if there's no measurement system on the pipeline in between, you can only be measured as one single unit. And then the final image would allow us to do one or two areas because we put a gate station in on that pipeline between two neighborhoods. So this is kind of it's not as much detail as we could get, but it's pretty close to describing how we would use op areas to define geographical data in previous studies. So we found that this can be a little bit limiting. So we've come up with a new level of detail. We accepted the challenge of not having super clear, specific, detailed data, and we tried to solve that problem. And so what we did is we're using the idea of granular data to now define sub-op areas. So we're taking billing data and or AMI data, and we developed methods to turn those pieces of data into daily data. So we're able to take somebody's bill, the number on their bill, and turn that into daily data for an area. What these sub-op areas allow us to do is to group these sub-op areas in different ways. So we're able to do tens, hundreds, or thousands of grouping in a traditional op area. The way that a way that you can understand this, for an example, in this cloud image to the right, there's these greenhouses, right? If we want to know characteristics of these green customers and how they're different from purple, let's say, we're able to do that now because we're able to look inside of what was just a one op area or big cloud before. So that's the kind of way that we're putting more detail to create deeper, more precise studies. Next slide, Dr. Brown. All right, so what are we going to call these more detailed studies that we're working on? We're going to call them granular studies. That's the kind of the method that we're using to come up with this data. So these are the basic features of a granular study. Dr. Brown will be talking a little bit to describe the mechanics and how it works, but this is top level. This image is how a very basic representation of what we're talking about. We're able to take an April bill, that essentially one big number on each bill, and break it down into the daily components. So we're able to look and see how customers are behaving on a daily basis from just their bill number. So we can use this work that we've done for hundreds of thousands or millions of customers. Like I said earlier, AMI or SCADA measurements can help improve accuracy, but they're not required, but they do help. And so we can use partial daily data to identify day of the week and other characteristics of the bills to help really define what those daily numbers would look like. With a complete set of bills and daily total loads, we're able to perform hierarchical disaggregation. And more on this later from the more qualified people to talk about it. Okay, so here I'm just going to talk a little bit about the granularity that we're able to achieve. And really, this is all down to what is available in the different billing data. So the things that we can sort for our different classes, including NASIC codes, we're able to define residential, commercial, and industrial granularity, sales numbers, transport numbers. We're able to break it down to residential subclass. We can look at different rates, different sizes, for example, looking at annual consumption of different groups. We can break it down by geographical location. If something we've been asked to do in the past is look at energy efficiency programs, so people who are enrolled in an energy efficiency program versus people who aren't, to help define demand. And then we have and, or, etc. If you have the data for it, we'll be able to break it apart as part of our study in granularity. All right, next slide. So I'm going to be talking about some of the scope of work of like our current catalog, what we've already done. Like we were saying earlier, there's a lot of custom stuff that we're able to use to address the modern problems that you might be experiencing, but these are the standard studies that we perform. So they're custom to each area, but they kind of provide a solution to a more general problem. And if you find yourself facing new challenges that you don't think are covered in this list, just reach out to us and we'll see what we can do to help. So our current catalog starts off with our most popular studies, I would say, which is Design Hour, Design Day, and Design Winter. So we're talking about there for a Design Day study is looking at the daily load on the 1 in 30-year cold day, the hourly load over the 1 in 30-year cold day. So that would be a Design Hour. And then Design Winter is something we've been recently asked to do, which looks at the load duration curves for the entire 1 in 30-year cold winter. And that kind of goes into the MCAS planner stuff that Jimmy was talking about yesterday. So if you're interested in developing that with us, let us know. We have a 1 in N year weather analysis, which kind of covers the geographical accuracy of the different weather stations that we're using. We have a gas month reports, which looks at daily loads out the next several months using different weather scenarios. So that helps with, mid-range planning. And then we have weather station optimization, which is really looking at the optimal combination of weather stations to use for a specific area instead of just picking, the one that's closest. All right, next slide. There's just a couple more things in our current catalog that I wanted to cover. We do annual and monthly loads out 10 to 20 years. So we use historical trends and weather scenarios, weather count forecast or customer count forecast, and we develop those for people, and they're usually used for a baseline for distributed energy resources type projects and reduction scenario impacts, things like that, that people are trying to plan deeper into the future so we can help accomplish those goals. The last two is our anomalous data detection and reconstruction. So this is us kind of going in and looking at your data, calculating what the load would have been had your system stayed on, or whatever might have messed with the normal flow of expected data. We're able to reconstruct that to be the expected load so that we can forecast based on that data. And then the final one we wanted to touch on was a couple of studies we've been asked to do about the impact and recovery of COVID. So that's something that we've been doing for a couple of customers. And if you have, if any of these studies in our current catalog seem interesting to you, or you have a more custom project you think we might be able to help with based on what I've talked about so far, like I said in Tom's talk, our info@Marquette Energy Analytics email would probably be the best place to send a message to, and then we can help you out with your energy forecasting needs. All right, that's all I've got in this beginning section. I'll hand it off to Dr. Brown. Thank you.
Yeah, thank you, Alex. You know, this is it's exciting because, you know, as Alex said, you know, historically we were doing these studies on an op area, a fixed set of customers, and being able to disaggregate bills into daily data has really opened up a whole new area of studies that we can do. A whole new area where we can get more information on what is being required in order for you to run your systems, or to be able to answer questions or fill requirements of your regulators. And so it's something that we wanted to talk about to let you know what we're doing. You know, the problem basically is that for an individual customer, you just might have bills which are going to be monthly or whatever, and quite often we need to forecast at a higher frequency than that, so that, you know, the best way to forecast something, you know, as we become, you know, in our scholarly work in forecasting, which you'll hear about this afternoon from Richard and Colin, basically you want to be able to have data that's at the same frequency that you want to make your forecast. But if we have monthly data and we need to forecast daily, we have that disconnect. So how can we address that problem? And it's a process that's known as disaggregation. We can do this by customer or by groups of customers, but basically we use weather. We build a model to break the bill. So what I have shown here in these rectangles here, this is the naively disaggregated bill. Naively, that's actually a term of art. We just take the number of days in the bill, and we the bill volume, and divide by the number of days in the bill, and that gives us the value each day. That's what I'm showing in the top graph here. What I'm showing in the bottom graph is that we've come up with a way where we've been able to take that bill, and using weather, we can break it up into something that looks much more reasonable, much closer to what we think the actual daily consumption was. And as Alex said, if we have some AMI or SCADA data, it doesn't have to be a complete set, but because quite often what we'll do is we'll get customers, we may have several years of bills, but in the last few years, we'll also have AMI data that will better allow us to figure out what the higher frequency signals are. For example, the day of the week characteristic. If you have monthly bills, you're not able to determine the day of the week characteristic from a monthly bill. But if you've got some AMI data of which you could then determine that day of the week characteristic, you can very easily infer that to the prior days, or to the bills where you do not have the AMI data. And not only that, even if we don't have any of that, if we just have some idea what customer class they're in and sort of what their day of the week characteristic is, we can actually put that into the process. And so this is just an example. Here is the, again, the bills naively disaggregated. Here it's after we've run it through the process. I'm also showing the scatter plots. And so you can see that, for example, this green bill here is the highest one. That was over a range of heating degree days. And so with the naively disaggregated, it's just going to be all at the same value regardless of the day. But with the disaggregation process that we have, the model-based disaggregation process, we're able to put it into a more typical load distribution. Don't worry about these dots down here. I actually didn't tell the entire story. These are not rectangles, these are actually trapezoids. Bills typically may not be read at the beginning of the gas day. In fact, actually, when we get a bill, we only know when it was supposed to be read. It might actually vary by a day or two, or it could be an estimated bill. And so these are actually trapezoids. And so you got to find the 2 points at the same level. If you add them up, it comes back into the scatter plot. One of the things we want to be able to do is to validate our methods that we develop. It's something we do with all of the things we do, and this is a validation on disaggregation. This is one of the data sets that we build. As I mentioned yesterday, I'm showing you it's not a real customer, it's actually multiple customers added together after they've been scaled by some random number in order to make it look like real gas. That's the blue line there. The jagged blue line is a good representation of daily data. And then the naively disaggregated, when we add up all those rectangles, that gives us this orange curve here, which is just piecewise constant. And so we're able to calculate, because we actually know the daily value, we're able to calculate the error in order to determine how good is this naive disaggregation. And I've got a weighted MAPE of 18.89 or almost 19%, or root mean square error, which wouldn't be useful to anybody because it's a fictitious data set, but it's at 73. So we're, 19% isn't the greatest. But then we run it through our algorithm, starting only with the monthly values. We didn't know what the daily values were at all. We did have the daily weather, and we're able to drop the weighted MAPE from that almost 19 down to 4.3. Or the RMSE, what was it, in the 70s, we got dropped down into 15. And so that's what we're able to do. You're asking, why am I using weighted MAPE? I was expecting more things here. Basically, get all those up there. For weighted MAPE, or for MAPE, the problem is that you're going to have this, for the same error, you're going to have a higher percent error on the low demand day. And so the typical MAPE becomes a warm weather indicator. It's going to be dominated by the warm weather, where usually we're more interested in the magnitude of the errors. When the volume is large, our typical summer flow might be 10% of what our design day flow is. We're more interested in what the error is in the winter time than in the summer. And so I've gone away from using MAPE. There's another problem here. As we start forecasting on more granular levels, depending on the customer class, we may have some days where the actual value is 0. And if you look at the formula here, it would be divided by 0, which is bad, right? You guys know that. So we've come up with, well, we didn't come up with this. This formula has existed for longer than I've been doing forecasting. Weighted MAPE, where basically it almost looks like the same formula, except we're taking the percent error, the actual minus the forecast divided by the actual, and then we weight it by the actual. And so if you look, the A sub I, in order to come up with the average now, because we have a weight, we have to sum up the weights, or sum up the actual loads. Instead of here, the weight was 1 if you think of it, so we have n of these, so we have to divide by n. So the A's cancel, and so here's the formula here. And so we don't, this weights the larger flows more heavily, which is what we want in order to come up with an indicator for weighs the winters more heavily. It also reduces the problem when AI is zero, the actual on the ith day is 0. Because see, the AIs have canceled, it gets the weight on the day where the load is 0 becomes 0. And so that removes that problem. But what's interesting is that one of the things we're doing with the disaggregation, especially when we're doing it by customer class, is we'll have the total load, which is a daily number, but then we'll have all the bills, which will be monthly numbers, but the bills are measured at the actual customer site. The daily number flowing into the op area is at the gate stations. There's the lost and unaccounted for. And that lost and unaccounted for could be both positive and negative. And the problem with, I've got the mate formula here and the weighted mate formula here. The problem with these formulas when the A sub i's could be negative is that this number, the sum of the A sub i's is going to get very small. And then some of these you're going to be weighting by a negative value. So it doesn't really make sense to use weighted mate with this formula when you have signals that can be both positive and negative. But we've made an adjustment to that by using putting in the formula here the absolute value of the load. And we have to put it into the summation here. Now the absolute values of the loads on the individual days is going to cancel. So we have this formula here. The only difference is from this formula to this formula is we've had to add the absolute values, but it does allow us to come up with a unitless metric for seeing how accurate our lost and unaccounted for would be in our disaggregation processes. So just a little side trip on error metrics there. And the only difference we've made is we put in the absolute value signs. And very importantly, this does not change the calculation of signals that are either always positive or at least non-negative. We have not changed the formula because the absolute value of a positive number is still a positive number. Another naive disaggregation that we've been working with is when we get aggregated billing cycle data. Typically a utility reads all their customers in a month. If you're a meter reader, you read one set of customers on the first of the month, another set on the second of the month, and so on, to the point that all the meters you read this month, well, half the gas, half the days were in the month you read it, where half the gas was used, half of the days that you used gas would have been in the previous month. But there are times when we only get one number per month or one number per month by customer class. And so we need to figure out, can we use this data? About typically half the gas would have been burned that month and half the previous month. And so what we do is, in a naive disaggregation, we just put together a triangle. So we got very little gas of that number was read in, the number was read in this blue, for this month in the blue square. Very little of it was burned on the last few days of that month. A whole lot more of it on the first days of that month and the last days of the prior month, where the first few days of the prior month, very little gas was burned. That's the naive explanation of how to use these bills. And so we end up with all these bills that overlap. These naively disaggregated bills, if you will, they're actually not bills. Well, I don't know if you want to call them bills or not, but they overlap because, you know, the bills, I'm looking at this purple one here, that's the meters that were read in February. A lot of that gas would have been burned in January, but also you read meters in January, which would have been read in December, and so on. So if we add up all those triangles, we get this orange curve here, and I've actually put the daily data stream. Again, this is validation data. Can we disaggregate this orange curve, or actually all of the triangles, the colored triangles? Can we disaggregate these so that it matches the, or is close to the actual? And so here on the top plot is the naively disaggregated. Interestingly enough, this is the same data set we looked at before with just the calendar month before. We're about the same weighted MAPE, actually slightly better weighted MAPE than RMSE. But when we do the model-based disaggregation, can't get quite as good, but I'm not surprised because the data is not quite as defined by its intervals, but we still have knocked it down to 7.3 weighted MAPE, or the RMSE is at 25. So it's an overview of the algorithm that we're running. With AMI data, there's a few other problems we have to work on. Typically, we get counts, which are going to be every 100 cubic feet. You know, the first tick that we get in a day, that was burned both in that day and the previous day, where all the rest of the ticks we get that day were burned that day. But if the previous day was 0, and then we get a tick, well, then we really need to spread that tick out over the prior, not just that day and the prior day, but the day before that as well. And on this data set here, see on June 6th, at June 26th, we got a load of 2. That second 100 cubic feet on that day was burned on June 26th, but the first 100 cubic feet might have actually started being burned back on June 22nd because we had 3 zeros in a row. And so in a way that also we have to disaggregate it. However, this gives us a much better, having the AMI data does allow us to get much better daily characteristics of our data sets. Alex mentioned that we've also come up with ways to handle anomalous bills. Well, there's 2 things going on here. One is if we know, you know, for example, when Winter Storm Uri hit, we lost power in Texas, and so we needed to reconstruct what the demand would have been had the power not been lost. That was a different replacing anomalous reads than what I'm talking about here. Here is we just have bills that we know are wrong. And let me give a few examples of that. And these are actual bills that we've been working with. We actually had the 2 gray ones here. We had a real high positive bill followed by a negative bill. And what this is that this bill was too high, and so the following month the bill was corrected, so it was a negative volume. Well, we don't want to disaggregate this real high bill and then the negative bill. So what we actually do is we roll those 2 together. So basically we just add these 2 bills together, and then we divide it over the 2-month interval to do the naive disaggregation. And then we're able to do the better disaggregation using that as our bill. And basically, we've combined those 2 bills into one 60-day bill instead of 2 30-day bills, or whatever the period was. We also see things when we have both AMI and bills where they don't match. The top one there, it's probably the AMI that's wrong because the bill looks much more reasonable. Where on the bottom one there, it's probably, this one was underbilled, and so they overbilled it the next month in order to equal it out. But the AMI is probably the correct, and so we've built in mechanisms to handle that. Quite often when we're especially working with commercial industrial customers, we'll have unusual things in the data sets where the characteristic of the customer, or the location, maybe the customer actually changes and it's the location that we're looking at. Residential customers, residential locations, when you change occupants, we do not see a big change in the usage characteristic. But when a commercial or industrial location changes customers, quite often we will see a significant change in the load. And so this is just, and I'm not going to go through all the details here, but we're able to detect a change point. And then using this PEDIT change point detection, which dates back into the 70s, it tells us where the change point is. Every data set will have a change point. This is done on the bills, by the way, not on the daily data, because we only have bills. But when we have a change point, we then look to see what does the average residual error look like before and after the change point. And if it's significant, then we say, you know what, there's a significant difference, and we're better off disaggregating this location as two different data streams rather than as one. That gives us a better model of what the load actually was. I mentioned loss that unaccounted for. We don't always know what causes it. Is it proportional to load? Is it proportional to pressure? Our meters not temperature compensated? It could be caused by a whole bunch of things, and you typically are going to get a value that is both positive and negative. But we're able to develop that data stream when we have all the bills and the gate station. There's also other interesting things when you look at individual bills. Sometimes you'll have gaps in the bill, which it could be a missing bill, or if the gaps are short, we're just assuming that the dates on the bill are wrong. We may have bills for a customer and the first several bills are zero. That means they probably took possession of the place but didn't get their loads, their processes ramped up until they had been there a while, and so we're best off when we're disaggregating those data streams to delete those. Or you've got the opposite case when someone goes out of business or moves away, where the last several bills are zero. We're better off removing those. And there's all sorts of other tricks that we do to improve the disaggregation. So basically, there's all sorts of fun things to do when you work with data, and we've worked with, now that we've looked at bills from several different customers, we've got a pretty good handle on how to disaggregate bills into daily, and we'll be able to do some studies.
There's a question when you have a second, Dr. Brown.
Okay, actually this might be a good time because I'm basically done with the overview. I've just got 2 slides to explain what the algorithms are for those that really want to know. Mm-hmm. And then we're going to talk to the application. So this is a good time for the question, Alex.
Okay, the question is, do you have all the customer, wait, let me see. Do you need to have all the customer bills to do a study by groups of customers?
It depends what the study is, but basically, it tells me that people are excited about this because I haven't even gotten to where I thought that one would have been triggered. Basically, the answer could be no, you don't need all the customers. For example, and I haven't gotten to it yet, but if you're doing an energy efficiency study and you want to have two sets of customers, one that the customers in an energy efficiency program and the ones that are not, so that you've got a control. You only need a representative sample of those, and then, because what you're going to do then is divide by the number of customers to see what the use per customer, how the use per customer has changed between the ones in the energy efficiency programs and the ones not in the energy efficiency programs. If you are in a situation where you want to know what are all the customers doing, for example, when we're looking at the impact of an energy efficiency program on the op area design day, then we just need the representative sample, but we would need to know how many are in there so that we could actually scale up that representative sample to match the total. Even though we don't have the total, if we only have half of them, then you'd want to double the impact of the energy efficiency program to see what the impact was on the design day. We'll get more into that in the next section. But that's a great question. Thank you.
All right, thank you.
I've got a couple slides, just a very little high-level overview. I mentioned that the bill is actually a trapezoid, not a rectangle, and so you can see that this bill was 655.25 for the month, and so we divided that by looks like 32 days. So basically, we divide it by 31 to get this much on 30 of the days, and then we put half of it on the first day and half of it on the 32nd day. And so that's the naively disaggregated bill. And then we build a model on all of the bills, all of the disaggregated so far, to see what the load would be. And that is it's the orange. It's not quite, but say it's the orange. And and we look at what the orange is over this interval, and it's only 551. So it's not what we want, because we don't want to violate the constraints of the bills. So we scale it up to the gold curve here, which has the 655. But then we move the gas around in that bill, but we take a fairly small step. This algorithm is what's called a greedy algorithm. It always thinks that all the errors are due to itself. Each bill thinks I'm the reason for the error. So we take a very small step, which is the purple curve. We then repeat this process on all the bills, and then we run through that process of making the model and adjusting the bills several times. There's a 2-minute overview of the algorithm. What's interesting is that something that we've developed this year is a hierarchical disaggregation, where basically if we have a complete set of bills and we have the daily total load, then we're able to do the lost and unaccounted for. And it's a process similar to what I explained on the previous slide, but when we build the model to think what the load should be, the orange curve here, we then do the hierarchical forecast, if you will, to adjust the model so that the sum of the models of all the different customers, because this would have been just one customer or one set of customers. We would have a model for all the sets of customers. We would adjust those models so that the sum of them equals the total load into the system. The advantage of that, well, it takes longer to do, but the advantage is the the sum of the individual data streams will be closer to the daily total, because you're not just aggregating over the month. The model now has the real day of the total characteristic into it, not just the model characteristic. It's going to better represent your peaks and your day of the week characteristic. And if some of the data streams have AMI data, because now all the models are going to be coupled, it will improve all of the disaggregated data streams, not just the ones with the AMI data. But maybe that's too deep into the weeds. Let me go over some of the studies that we've done. As I mentioned before, here I don't have all the neat little houses here. I just have circles in my cloud. But basically, we're able to do the disaggregation by any grouping of customers that we want. We can do it by customer class. We can do it by rate, geographical location, whether they're in a program or not, on and on and on. And we can divide this just into a few, or we can even divide it into, for very large utilities, we can even divide it into tens of thousands. And then we can perform a host of studies. For example, once we've got, say, a small residential, single-family residential class, we can then do a design day study on that single-family residential class to see what they're doing. This is a result from one of the studies I think I showed this probably last year, where we did the impact of COVID on dividing by the NAICS code. I think it's pronounced NAICS. NAICS 72, the two-digit NAICS codes, the accommodation of food services. This blue line here is March 15th of 2020, when we all started staying home. When we all isolated, or what was the right word? Anyway, we saw that the accommodation food services was big high. It was higher in the winter than in the summer, but this orange line here is from March 15th through the end of the year of 2019. And then COVID hit, and this is the response of the accommodation food services. This is zero down here, so you've lost a significant part of the load. Here I've got this scale so that the load March 15th to the end of the year of 2019 was at 100. Now from March 15th to the end of the year, in the impact of COVID, that was down 36.6%. For accommodations and food services, you're probably not surprised that that load would be impacted. But we're able to do the analysis by however we can divide the customers. In this case, we have the NAICS codes. Here is the energy efficiency program analysis, where we divided the customers into two groups. So this is the example I was talking about earlier. We don't have to have all the customers. This is just a per customer analysis, and this is fictitious data, by the way, because actually when we do the actual data, they wouldn't actually line up here, because they won't be a perfect match between the ones with the control group and the ones with they're actually in the program. But it illustrates the point, and that is, we see that and this is typical, that with the energy efficiency programs, we see their use per heating degree day. This is therms per heating degree day in the top chart. By the way, this is the adoption into the program. It starts out at 0 and comes up to 100%, following some curve. Typically what we're seeing is that the use per heating degree day decreases with customers in this particular energy efficiency program, but interestingly enough, their base load increased. But overall, their usage did decline significantly. But we're able to do that analysis with the bills on sets of customers. And here's where we're looking at the impact of the energy efficiency program on design day. So the backcast of the design day are the blue diamonds, and then the forecast is the black diamonds, and that has incorporated into it the actual energy efficiency programs that have been running. And so we're able to, knowing the impact of the energy efficiency programs and how many customers are in each, we're able to actually say what the design day demand would have been if we had not done the energy efficiency programs. And that's the red curve there. We can actually do a backcast of that starting when the program started and then project that out into the future. We can also work with you to figure out what the impact will be of future programs. And so that's illustrated by the green curve here. The black curve has built into it the impact of the trends of the adoption of the energy efficiency programs. So we want to be clear what that is, but then we can work with you to figure out what else is going to happen, or even what if scenarios, in order to figure out what the load would be on design day or also annual, with the impact of other programs. Which is what this is showing. We have using an ensemble of economic models, proposed policy impacts, and other economic variables. We're able to forecast monthly loads for each of the next 10 to 20 years. And that would be the black curve here. By the way, there would be some real stuff in this first one. That's why it's slow. The black curve here would be using 20-year normal weather. But then we're also able, as we talked about yesterday, if we've got 74 years of weather, we're able to evaluate those models using the 74 years of weather scenarios. And so we not only get what we think the expected load is going to be going out 10 or 20 years, we can also get what the distribution might be based on weather, because the weather's not going to be normal. And with these, we can also dial in impacts of future things that are going on, whether it be energy efficiency programs that are going to go in and electrify a neighborhood, or you got we've done some granular studies where we're looking to see what happens if we put in a new large industrial customer in a system. What is the demand on that system going to be? So the utility is able to figure out if they've got the infrastructure in place in order to supply that customer, things like that. We can do all sorts of evaluations that way. As Alex mentioned, we can also, if we've got a sub area, if we divided the opera area into smaller geographical areas, we're able to come up with the local weather. We do the weather station optimization in that smaller area, and then we're able to do our 1 in 30, for example, 1 in 30 year analysis, even look at the impact of climate change like we discussed yesterday. And so any questions before I turn it over back to Alex?
There's a question, Dr. Brown. It's asking, are there references on the disaggregation algorithm?
This is an algorithm that we've developed. An awful lot of the references that are in the literature really don't apply to this. We've had to develop, well, we first started developing this many, many years ago when we were getting the gate stations were not read daily. 25, 30 years ago, gate stations may not have been hooked up to the SCADA system, and so someone would have to go out and read them a couple times a week. And if it was a holiday or the weather was bad or something, they would reading would be skipped, and they didn't read all the gate stations on the same day. And so the traditional disaggregation algorithms that you find in the literature didn't really apply. I'm trying to remember if we've published a paper on this. I don't know if we have, but we have had several students work on this at Marquette. And so we probably have thesis and dissertation. And I'm not positive, but Colin may be speaking on this afternoon.
Yep, I can do a quick plug for Colin's talk. It's forecasting natural gas demand using hierarchical, that's a hard word.
Okay, that's probably not
framework.
He's doing some various things. He's doing more of the hierarchical, which I talked about in the disaggregation algorithm.
Mm-hmm. Yeah, that should be a good talk.
So I'm excited about this because we're able to do studies at a much more granular level, and this is being asked by commissions. If we're able to do it by customer classes, by rates, smaller geographical regions. If we're worrying about does the infrastructure support it, what happens, we've got an aging infrastructure and we don't want to build a lot more pipe. What happens if we take this pipe out of service? Are we still going to be able to meet the design day in this geographic region? We're able to help utilities solve those problems. So I'm going to turn it back over to you, Alex.
Okay, thanks. Yeah, we can go to the next slide then. All right, so I'll be closing up the talk today. If you guys have any more questions for Dr. Brown, just feel free to put them in that questions box in the control panel menu. And after I go through, I'll be sure to read them off to Dr. Brown. And I just want to remind everybody that we're available for consulting, further research, making new phases of past studies that we may have done for you. So if there's any work that you're interested in getting some help looking into, let us know. I'm just going to real quick summarize what I talked about earlier. This is everything just pushed down to one slide, talking about some of the different studies that we do that can be done by customer groupings. So design day studies, design hour studies, which is looking at that 1 in 30-year cold day and the hourly load over that day. We have the 1 in year weather analysis, which looks at what is the expected 1 in 30-year cold day, the 1 in 30-year cold winter, what's the impact of climate change on your 1 in year weather analysis, helping prepare for changes that might be coming. We also do weather station optimization, which helps refine that weather data that we're getting and using. We have gas month reports, which is the monthly scenario. So we're looking at several months for daily loads. We have annual and monthly loads out 10 or 20 years, which is the long-term planning. Then we have the impact and recovery for COVID and anomalous data detection and reconstruction. So just real quick, that's our current catalog, like I said earlier. You can go to the next slide, Dr. Brown, and I'll be talking about some of the custom studies. So this is some of the work that we think might be helpful for people to hear about, because we have this new level of detail that we're achieving with these granular studies. We can now tailor for some new needs that we might not have been able to help with before. So understanding the needs of new developments, like Dr. Brown was saying, if you're adding new pieces to your puzzle of pipelines and users, then we can help understand the needs that might be coming. If you have an area that's been mystifying in the past and hard to understand, we can look at the billing data that comes in and help demystify that area. We're able to provide insights to determine where demand will increase or decrease to, again, help prepare. we're able to support our customers in fulfilling regulatory requirements. So that might come from a consulting angle, or if there's pressures they're putting on you that are new and changing, just let us know and we can probably help figure out a good plan forward. So measuring the impact of energy efficiency studies, like we've been talking about, we've been asked to do that, and we're able to produce good work on that. So if you have any energy efficiency studies that you're interested in having us take a look at, reach out. And then we also help plan for moratoriums and energy transitions using these granular studies and the spilling data to really get down to, you know, block by block or neighborhood by neighborhood, what that energy transition might look like. And we can do a lot more. So like I said before, reach out to us if there's any challenges you're experiencing when it comes to this kind of energy planning. Chances are we'll be able to make a study to help take care of some of your challenges. And finally, my last slide is, it does not have to end here. The unique work that we have done for customers, it's been brought to us. That's how we develop these new techniques and why we have the catalog we currently have. That's the things people have asked us to do. So with the new level of data we can achieve, like I said, we can custom tailor these studies to your needs. And I've already gone through that list, but it's there again in case you're wondering. If anybody has any questions, please put them in the chat bar. There's one more for Dr. Brown, which is, please explain what the hierarchical, that word again, disaggregate. Yeah, and Colin
talk about that this afternoon. Basically, if you've got the simplest way, a simple example is if you're forecasting both daily and hourly. You've got hourly models and you've got a daily model, and you forecast what your load is going to be. If the models are built independently of each other, you would not expect the sum of the 24 hours from the hourly forecast to equal the daily. And they'll be close, but they won't be the same. And so the idea between hierarchical forecasting is that you can blend those blend is the wrong word, but you can it's a post process that makes the sum of the 24 equal the daily forecast by adjusting all the 24 and the 1 forecast. So and the idea is by blending those together, you're going to end up with all the forecasts are going to be better. You're not just making one equal the other. It's a technique that makes them all better. And Colin, apparently that's what he's talking on today. He has a lot of expertise in that area.
At 1 p.m. Central, just so everybody knows.
So with the hierarchical disaggregation, we're doing something similar. We've got the daily total, but then we've got the different customers or customer classes monthly. But we're building a model to do the disaggregation, so we come up with a daily model for each of those customer classes. Now that's a spatial hierarchy rather than a temporal hierarchy that the hourly to daily is, but that's a temporal. But this is a spatial because we've got all these customer classes. Here on my fingers here. I don't know if they can see me. Where all of these are supposed to add up to the total daily into the system. And so with the traditional disaggregation we've done, we do not have that we're not penalizing that in the disaggregation, the mismatch between the sum of the different bills and the total. We're now, with the hierarchical disaggregation, now we're taking that into account. And so we're getting a better disaggregation. And that also allows us, if we need to be able to determine loss found unaccounted for and things like that, we're able to do that. So a long answer, but.
Yeah, I think that's good. And then, yeah, we should leave some for Colin to talk about this afternoon. He'll have plenty, but I think that's a good intro for him. So we're a little bit early here at 11:12. I don't see any other questions coming in. So I think we're okay just to go to the next slide and wrap this up and give everybody to lunch a little bit early. Just some reminders here, some office hours information. So we like to discuss, we like to talk, we want to hear what's going on, the other side of the forecast. So please reach out to us so we can discuss and talk about these topics and hear what's going on with you guys. So Ron Brown, his information's over there on the left, and my information's over on the right. You can reach out to either of us, and we'd be happy to talk and discuss different things.
Yeah, and I would encourage you to do this because, as Alex said, that the ideas for these studies has really come from you guys. If we can help you out, Tom yesterday mentioned that this project started in 1993, so I've been doing this 30 years, and I would quite often walk into. Back then, it was the Wisconsin Gas Company. Work with the people there. They're the ones who taught me the gas industry. And at the end of the meetings, I would wander into the control room and sit there and talk to the old guys in the control room and listen to their stories and figure out how to help them. Now I am one of the old guys, but I still want to hear your stories. And so,
yeah,
please reach out to us. Thank you.
Yeah, there you go.